As we get into this last chapter, we're going to first talk about a concept called heat. Now, this topic in physics, heat in physics, has a different definition than we use in our everyday life. We do not mean temperature. It can certainly be related to temperature, but heat is actually an energy transfer. Now, if we think about conservation of energy that we used before, all of the potential energy initially in our system, plus the kinetic energy, plus any work done by something other than gravity or the spring, some sort of external force, would equal potential energy final, kinetic energy final, plus the change in thermal energy final. Now, so far, up until now, we've attributed this delta E thermal solely to friction. That is not the only situation. The delta E thermal is related to the temperature, and specifically to the change in temperature of a system or a object. Up until now, it was the kinetic friction that caused that temperature change. But we will be talking about gases and other ways in which we can have temperature change. Now, heat is another way of transferring energy similar to work, and so it actually needs to be added to this left side of the equation. Now, we are going to use Q to represent the heat. Heat is a transfer of energy between a system and its surroundings. It's different than work. Sorry, let me finish that thought. So heat is a transfer of energy between a system and its surroundings. Now surroundings. Work, as we've talked about before, is also a transfer of energy. Work, though, is a transfer of energy as forces cause displacement. We call this a mechanical transfer of energy. And so work still totally force acting over a distance. Work is still F dot DES. And so it is one way to transfer energy between a system and its surroundings. Positive work, meaning energy in to the system. Negative work, meaning energy out. Heat, we're going to define as positive, meaning energy in. Negative, energy out. But the mechanism, at which the energy is transferred is different. So energy is transferred because the system and its surroundings are at different temperatures. So for example, I like to have ice water around. And so I fill my glass up. I've got ice cubes, I have water. If I'm at home, I just have a big plastic cup and I leave it on the kitchen counter and I get a drink every now and again. But the longer it sits, so over time, if I haven't been drinking the water, and it's just sitting out, the ice ends up melting. And if it's out there long enough, the water warms up. It doesn't stay cold all day long. I don't often leave it long enough to get cold, but for this purpose, to talk about heat, we have to talk about enough time passing for this energy to be exchanged. In order to melt ice and warm water, that takes energy. So energy is transferring into the system, affecting the bonding between the molecules. That bonding or break in bonds can cause the ice to melt or the liquid water to warm up. And so heat is because the surroundings, in this specific case, the surroundings, the room in which my ice water is sitting, is warmer and energy naturally transfers from a warmer system to a colder system. Now, this heat is something that takes some time. Another example is to put a pot of water on the stove. You want to boil noodles or something, and you turn on the stove. Whether it be flames from the gas stove, the electric burner heating up, an induction stove, this is hot. And that heat, that high temperature causes energy to flow in to this system of the pot and the water, causing the temperature to increase. And so heat in general is always a transfer of energy, but it's a transfer of energy because a system and its surroundings are at different temperatures. So it's a different mechanism than work, but it is still a transfer of energy. And we are going to use the definition similar to work. A positive heat we're going to use as energy going into the system, negative work as energy coming out. Now we're going to have two fundamental equations to start with that we're going to talk about with heat. And that's going to be the energy required to change temperature of a material. This equation looks like this. So again, Q is the symbol we're using for heat. The equation looks like this. So M is going to be the mass of the material. C is called the specific heat. Sometimes you'll see it specific heat capacity. We often abbreviate that as specific heat. This is a constant, or more or less constant for our purposes anyway. This is a constant that is specific to the material itself. If you end up taking thermodynamics, you'll find in certain temperature ranges the values do change slightly. But for our intents and purposes, we're going to just use the constants that were given. Delta T is specifically the final temperature minus the initial temperature. So delta T is positive if the final temperature is greater than the initial temperature, which means Q, the heat, will be positive as well. So in the case that we're changing the temperature of a material, if we increase its temperature, heat is added. So heat is added when temperature is increased. And then the opposite is true. Heat leaves the material and goes to its surroundings if the temperature decreases. But heat does not always result in a change in temperature. This energy could go into changing the phase of the material. So the energy required to change the phase. So if you remember phase, we mean whether the material is a solid, a liquid, a gas. That's what we mean here. This equation is plus or minus. We have to choose the correct sign. So positive means energy going into the system. Negative means energy coming out. L is called the latent heat. There's two different types of latent heat. You'll see a latent heat of fusion. So L sub F is the latent heat of fusion. This means the solid and liquid state change, whether we're going solid to liquid or liquid to solid. The difference would be the sign. If we're going solid to liquid, we're putting energy in. So solid to liquid would require a positive Q. We have to put energy in to start breaking the bonds between the molecules that can then allow the temperature to increase once everything is melted. Vice versa is true. If we have liquid and we want it to become solid, we need to take away energy. And so that would relate to a negative Q with our equation. The other latent heat, L sub V, this is the latent heat of vaporization. Vapor or gas, this is between the liquid and gas state. And to go from liquid to gas is a positive Q. So liquid to gas, that would require energy going into the system. If we're condensing gas back to a liquid, that's energy coming out of the system. So these two equations we'll look at to find and relate to the energy needed to change temperature or change phase. Now in the test notes, we have a table that allows us, that has specific heats and latent heats. Let me grab that. All right, so I copied in this table. This is, I think it was on page 3 of the test notes. This is the same table we've been using for density. This column is that specific heat or specific heat capacity. So for example, water has a specific heat of 4190. The units up here at the top. So for water, just writing this over to the side, 4,190 joules per kilogram Kelvin. That means 4,190 joules of energy are needed to change the temperature of 1 kilogram of water by 1 Kelvin. That's what that means. Looking through this table, it's not by any means fully comprehensive. It's from the table in the book. But notice water is rather large. That's a large value compared to the others. And water is actually really, this is one reason, for example, if you're near coastal regions or near water, the temperatures don't vary quite often as much as it would away from water. And that's because the water can absorb energy and give off energy, and it has a lot of it. It takes a while for that energy to exchange. This column, T sub m, is the melting temperature of the material. L sub F is that latent heat of fusion. Oops, sorry. I might make it easier to see though. T sub B is the boiling temperature, so the temperature at which we can change from a liquid to a gas phase. L sub V is the latent heat of vaporization. Resistivity is for physics too, so you don't have to worry about that column. And sorry for the little symbol in the middle of the diagram. That is just because of the recording software that I'm using. Now keep in mind, notice ice and water are separate. And that's because they have different specific heat values. It sometimes throws students off to see the line for melting temperature and latent heat of fusion, but it's the same values because we're just changing phase between a solid and a liquid when we're going from ice to water or water to ice. So those values are listed simply just with water. So this table will come in handy. I want to do one example as part of this video, and then I will do a few videos as well that are additional example problems. All right, so let's just go through this question here. So which requires the most energy? A, we're going to raise the temperature of 1 gram of liquid water to 50 degrees Celsius. Melt 1 gram of ice, so still water, but in the solid state, so melting it at a temperature of 0 degrees Celsius, or raise the temperature of 1 gram of ice from 223 Kelvin to 273 Kelvin, so that's below freezing, which is why it's ice, a solid form, and finally to vaporize 1 gram of water at a temperature of 100 degrees Celsius. So actually, let me pull this down a little bit because we're going to be using these values up here. I'll copy them down below. When we look at the water line, we have C for water, meaning liquid water, is 4190 joules per kilogram Kelvin. Ice, C is 2090 joules per kilogram Kelvin. The latent heat of fusion is the 3.33 times 10 to the 5th joules per kilogram. And the latent heat of vaporization is 22.6 times 10 to the 5th joules per kilogram. We're not going to be able to read those off the table when I slide that back up. All right, so A, we have liquid water. Now we tend to just, when we talk about water, assume liquid, but of course water itself can be in a solid or gas phase as well. And so that's why it's specifying. Since we're changing the temperature of the water and not the phase, we're going to use the MC delta T. And because the C value has units of joules per kilogram Kelvin, we will want this mass to be in kilograms. So 1 gram is 0.001 kilograms. Our C, our specific heat, is 4190. Now, it's not telling us which temperatures we're changing between. We're just changing by 50 degrees Celsius. If you recall from earlier video, a change, a delta T of 50 degrees Celsius is the same as a delta T of 50 Kelvin. And that's because the conversion of adding 273 to both the initial and final temperatures, when we take delta T, we get the same difference. The kilograms are going to cancel, the Kelvin's going to cancel. So the energy needed, plugging this in, 209.5, so essentially 210 joules is needed to raise this temperature by 50 Kelvin, or by 50 degrees Celsius. And this is 1 gram, this is not a whole lot of water. So B, we have the same mass, but we're going to melt this ice. So this water is in solid form. It's at 0 degrees Celsius, which if we scroll up here again, the melting temperature of water is 0 degrees Celsius. So this ice is at its melting temperature, which it needs to be in order to then be able to change phase. Since we're simply changing phase, the equation we're going to use is the M times L. To go from a solid to a liquid phase, which we're melting, that's what we're doing here, we need to put energy in. The mass, we need this again in kilograms because L has units of joules per kilogram. Now we specifically want L sub F in this case. The fusion, L sub F, the latent heat of fusion, is specifically for the solid to liquid state. And that's what we're doing. We have a solid, we're going to melt it. We want it to become liquid. And that's why we want L sub F. So the energy needed here (333 joules). So, well, we don't even have 2 sig figs, so, but I rounded A to 2 sig figs, so I'll round this one to 2 sig figs. So it takes more energy to break the bonds to be able to change phase from a solid phase to a liquid phase than it did to change the temperature of just liquid by that 50 degrees, which is a big change in temperature. All right, let's look at C. C, we have ice. We have 1 gram again, and we're changing the temperature from 223 Kelvin to 273 Kelvin. So 0 degrees Celsius is the 273. If I take the 223 and minus 273, we have negative 50 degrees Celsius. So our change in temperature, we mean final minus initial. So 0 minus negative 50 is going to be 50 degrees Celsius, which is also 50 Kelvin. So the energy needed to have a block of ice, well, a tiny cube of ice, I guess, because it's only 1 gram, and change its temperature. Because the final temperature is the melting temperature, this is it's a really, really cold block of ice being brought up to its melting temperature. It's going to stay ice the whole time. All we're doing is changing its temperature. So we would talk MC delta T. None of it would melt. We're looking only for the energy needed to get it through this temperature change. Now C is different when we have ice instead of liquid water. So these kilograms are going to cancel. The Kelvin are going to cancel. But, so we essentially have 100 joules of energy are needed to bring this 1 gram block little cube of ice and change it by 50 degrees while it is still ice. So less energy is required to change the temperature when it's in this solid phase than when it was in its liquid phase. D, we're going to vaporize 1 gram of water at 100 degrees Celsius. This is the boiling temperature, meaning it is the temperature at which that phase change starts to happen. Now, total side note, we are assuming that the pressure is 1 atm. All these values in the table are making that assumption, and we'll run with that. So we have essentially boiling water. So this question wants to know how much energy is needed to boil off 1 gram of water if it's already at its boiling temperature. So we need only the change of phase equation again. This time we'll use latent heat of vaporization because we're going from the liquid to gas phase. And we do need to put energy in to go from a liquid to a gas. So taking our latent heat of vaporization, multiplying it by our mass, and I suppose I really don't need a calculator for this, but I just used it. So there you go. Look at that. That is a huge value compared to any of those other three. It takes a lot less energy to melt a little cube of ice than it does to boil off the same mass of water. And that's because of these different constants and latent heat in that case. So any problems that we're going to be looking at, we have to consider what state, what phase the material is in, whether we're only changing the temperature of the material or if we're also changing phase. A material does not change temperature while changing phase. Now, in small, tiny regions, if you really zoom in, there might be little tiny regions that are changing temperature because they're farther from, say, an ice cube. We're just going to look at a material as a whole and the energy required in any given problem. And so we have to think of the energy required to change temperature separate from the energy required to simply change phase. And we want to keep in mind that those are two separate things. So for example, this part C, where we brought our ice from negative 50 degrees Celsius to 0 degrees Celsius, the energy we found here, this energy only changes the temperature. There's not enough energy to start melting the ice as well. Even though ice melts at 0 degrees Celsius, that energy is not enough to actually start melting it as well. It only was enough to change temperature. So I'll be doing a number of examples for you. So make sure you're going through to see and recognize these energy changes and when to account for the different equations. Some of the problems will be similar to what we just did, how much energy is needed to do something. Some of the problems are going to be called calorimetry problems. Calorimetry problems are materials in an insulated container. This insulated container is called a calorimeter. If we put a few different materials into an insulated container, the purpose of the insulated container is to not allow energy to transfer between the system and its surroundings. I love my insulated water bottles that I take with me because the water stays cold for much longer than it would in my plastic cup at home sitting on the counter. When we do this and put different materials into an insulated container, the energy will exchange between the materials themselves. And so if we were to add up all of the heats, so any materials that are losing energy because they're cooling off, or any materials gaining energy because they're warming, all of the energy exchange will be between the materials within the container. And so we can relate that and use that concept of essentially it's a conservation of energy within the system itself, and look for a final temperature. Or you could wait and find the final temperature and work backwards to find how much of a material you had, or the specific heat of material. We wait until a thermal equilibrium is reached. If you've ever done a calorimetry experiment, they are incredibly boring because you put these materials into an insulated container with a thermometer and you have to just sit and wait and wait and wait, because it takes time for this energy to exchange between the different materials. But what we mean by a thermal equilibrium being reached is that one final temperature is reached, meaning everything, all the materials in the container, ends up with the same final temperature. So you're watching the thermometer until it's not changing anymore. So very boring experiment to do, but can be useful to figure out specific heats of materials or how much material you have, that type of thing. So as we go through the example problems, so separate videos, look for the different types of problems. They're either going to be ultimately asking for how much energy needed to do something versus materials put together in an insulated container and coming to a final common temperature.